All right, for this video, it is time to start programming the rotational dynamics. So we have here the initial conditions for translational dynamics, and so basically we need to say initial conditions position and velocity, and now we're going to say initial conditions for rotation and or attitude and angular velocity. Okay? Oops. Now what I want to do is I want to make a phi 0, a theta 0, and a psi 0, and basically do a PTP 0, which is a phi theta psi, and call that phi 0, theta 0, psi 0. And what I want to do is I want to make a function that gives me my quaternions taking Euler angles to quaternions. And I want the input to be PTP 0 in this case. And this is going to be 0, Q. So that's the 4 quaternions. And then these are the 3 Euler angles. The equation for this is here. So if I take these Euler angles, and again, this is in my, my spaceflight mechanics PDF. So if I take these Euler angles and plug it in, I'll get the quaternions. I totally forgot that I have all of these routines already in MATLAB. And so if you go to the folder 6DOF, a lot of these routines that I'm going to use today are already in here. So here's Euler to quat. So I'm going to copy this. I'm going to open up a new folder. And I'm just going to copy this in here. And the reason why I'm going to do this is because I want to make sure that you have everything you need in this folder. So this is going to be Euler angles to quaternions. And let's see, so I'm going to open this up. And we're going to say Euler angles to quaternions. And then I'm going to say phi theta psi is my input. And I'm going to do phi theta psi of 1. And the other reason why I want to do this is because I kind of want to make this code a little bit more intuitive when you open this. Phi theta psi of 3. And then you use those. If you look at these equations here and these equations here, they're the same. I could probably optimize this a little bit, but I think I'm just going to leave it. And I think that's it. So that will give me my quaternions. So let's run it and make sure that that works. I also added some print statements in here because you need to make sure that you have the IGRF model. But yeah, it looks like everything's still working. Still got the magnetic field model. Okay, so now that we have the quaternions, now we can do the angular velocity. And so we can do P0, Q0, and R0. So that's the angular velocity of the satellite. And then now I can just throw this in here. Q0, 1, 2, 3, and then P0, Q0, R0. And now if I run this whole thing is going to completely bust. And it's because the satellite thinks that the state is only a 6x1 when now it is a 13x1. And so we need to do the kinematics here. So we can do translational kinematics is here. And then we have to do rotational kinematics, which basically says we need to compute the derivative of the quaternions, and the derivative of the quaternions is here. So we need to generate this matrix here. So what I'm going to do is I'm going to put this over here and this over here. I don't think I have this function already built. So first I'm going to grab my quaternion vector, and so that's going to be state of, I think 7, 8, 9, and 10. 7, 7, 8, 9, and 10. Yeah, that's 4 variables. And then, oh, what happened here? It looks like a Java issue. Uh-oh. Is that on the screen? Okay, what if I keep typing? Okay, what if I save? What if I close this? It's still there? Seriously? Okay, I'm going to pause the video and bring this back. Okay, and we're back. So let's see, where was I? So we have the quaternions. So now we need to make this big PQR matrix. Again, I'll put this over here. So now we need to make this big PQR matrix. So first we need to get P, which is state of 11. Q, which is state of 12, and then R, which is state of 13. And then we need to make this big matrix, so I'm going to call this PQR mat. And let's see, it's 0 minus P minus Q minus R, P0 R minus Q, and then Q minus R 0 P, and then R Q minus P 0, and that's it. So then Q0 1 2 3 dot is 0.5 times PQR mat times Q0 1 2 3. Okay, so that should be the kinematics, and we should be done there. So then down here, I just need to add Q0 1 2 3. Okay. Then we get into the dynamics. So let's leave the gravity model, let's leave the magnetic field model, and then let's get into, here we got the translational dynamics, and then we're going to do rotational dynamics. And I'm just going to program this in. It's not going to be completely right, but there it is right there. So it's PQR dot is equal to the inverse of I. And actually the inverse of I is a constant. So I'm going to, yeah, because I could save a lot of time if I pre-compute this. Should I make, I'm gonna make inverse I a global, and I'm gonna do it ahead of time. Okay, so inverse of I is gonna be a global times, and then I need, this is the moment from the propulsion system, this is the magnetorquers and this are reaction wheels. We're just doing magnetorquers, so I'm just going to grab this term here. Let's see, so I'm going to say LMN magtorquers. And then up here, I guess I'm going to need magtorquer model. And this is going to be the current. I'll code this later. So I'll say magtorquers for now is just 0, 0, 0. I'll code that later. So there we go. So then we need PQR. We need cross. Is it cross or cross 3? Cross. So if I do cross 1, 0, 0, crossed with 0, 1, 0. Okay, cool. All right, so it's just cross. So it's minus cross PQR with angular momentum, which is H, and then minus I dot. I'm assuming I dot is 0. So that's it. So that's done. So I don't think we need this anymore. So now we just need to fill in what I left off. So first of all, I need PQR. So PQR, and actually let's define, I like defining my states up top. So like these, let's pull these up here so that everybody can use them. Okay, and then let's, it doesn't look like, it's giving me, oh, okay, because I need to put the dot there. I was wondering why it was giving me a little error there. And then I may as well, now that I'm down here, type in PQ0 dot here. So up top, I have PQR individually, but I also need PQR all together. So that'll satisfy this requirement. H is going to be inertia times PQR. So I need to define my inertia. So I'm going to go ahead and just make inertia a global too. And then while I'm at it, I'm going to just go ahead and make M a global. So then what I'm going to do is I'm going to create a, is inertia a variable? Yeah, oh, no, it's not. So I'm gonna make a script really called inertia, and I'm gonna throw this in here. I'm gonna say I is 0.3, 0, 0, 0, 0.9, 0, and then 0, 0. I guess I need to make it symmetric, so let me make it 0.3 along x and y. Let me make x and y big, make it a prolate object, like a cylinder, and then the z-axis will be the smaller axis. So it'll be like, you know, like the x and y are the same, but then the z-axis is different. And so I'll make this like 0.3. And then inverse I is just inverse of I. So this is, let's see, inertia in kilogram meters squared. And then, that's the inverse there. And then over here, let's see, I need to open up, let's do edit main. Oh no, I'm in the wrong directory. Shoots. Let's open main, and then let's run this, and then change folder, and then it's going to throw an error, which is fine. I don't even care what the error is. And then I need to, let's see, copy, delete, and then edit inertia. And now it's going to tell me that it doesn't exist because it's in a different folder. I'm just going to paste that in, go back to main, make m inertia and inverse inertia a variable, and then after planet, I'm going to get mass and inertia properties, and I'm going to run inertia. Okay, I want to say that's it. Let's give it a go. Main. Oh, buddy. Let's see, this is not consistent. So what is Q0, 1, 2, 3 of 0? Ah, it's a column, it's a row vector. So where's my Euler angles to quat? Okay, that's why. Let's just throw a tick mark here to make that a transpose. And then we should be able to, yeah. Oh, nope. Let's see, matrix dimensions must agree. So let's just debug this. Let's just throw a debug point. Where is this Q0? Oh, I can just click this, can't I? Beautiful. So let's throw a debug point here. Type in main. So PQR dot is a 4x4. Q0, 1, 2 is a 4x1. I don't see an issue here. Okay. Everything looks okay so far. How big is D state? So 13 by 1. No big deal. Okay, so step. Oh, I did not want to do that. All right. It looks like everything's fine now. I'm not sure. Let's get rid of that debug point and run main again. It looks like it's not happening in the first rotation. So let's actually get rid of this semicolon and hit F5. Oops. Oh no, I don't want to do that. Main. I want to run main. Yeah, Q03 dot, Q10, 1, 2, 3 dot is a 0. You know what, I probably need to, let's spit out PQR mat and Q0, 1, 2, 3. Oops, hit F5 in the wrong one. This is an interesting bug here. Okay, yeah, why did it become a row vector, like randomly? Yeah, see, it's like a column vector, and then all of a sudden it just randomly becomes a row vector. Do I pause the video and try to fix this, and then tell you what happened? I'm gonna pause the video and come back. Okay, I figured it out. What's happening is here. So when you run OD45, this is a column vector, and when you run d state dt, it becomes a row vector. That is a row. So we need to send it the transpose, and then I think I can get rid of this here and this here, and now I can run this. It was in the second loop that it was throwing the error. That's why I didn't catch it in time. All right, it's taking a lot longer because I'm integrating 15 or 13 states now. So if you notice the translational dynamics, nothing changed. Everything's exactly the same. So what we need to do now is we need to plot the rotational dynamics. So let's do that. So convert state to kilometers. So that's actually wrong because I only need to do all the rows, and I just want to do columns 1 through 6, which is the position and velocity. Okay, and then the 7 through 10 is going to be my quaternions. So let's do extract state vector. So Q0, 1, 2, 3 is going to be state out of all comma 7 through 10, and then PQR is going to be state out of all comma 11 through 13. Now, what I also want to do now is I want to convert, because quaternions are kind of weird, I want to convert my quaternions back to Euler angles. So I want to use this function here. And like I said before, I'm pretty sure I have this already. Extract Euler, extract quaternion. There it is, quat to Euler. So I'm going to paste this in here and rename it quaternions to Euler angles. But I'm going to edit the function so it does exactly what I want. So I'm going to get rid of iplot and the body name and all this stuff, and just give it Q0, 1, 2, 3, and call it quaternions. And I'm going to assume that the input of quaternions, to Euler angles, and I'm going to assume that the input is an n by 4 vector. I'm going to get rid of this. And oh, is that right? Is it an n by 4? So if you look here, this is all by, yeah, that's an n by 4. Okay, cool. So n by 4, so this is right, and then this is right. Don't I need to like initialize PTP, or is that gonna work? I don't need this. It looks like I need to make like the real function or something. I don't need any of this iplot stuff. Let's just see if that works. So if I do and let me make this out, and then PTP out is quaternions to Euler angles of Q0, 1, 2, 3 dot out. Okay, and then we're going to make an earth plot 3D orbit, plot the magnetic field, plot the norm. I want to plot Euler angles. Let's see, am I recording here? I am. Let me pause it for a sec. So I'm plotting Euler angles, so I'm plotting, let's see, plot T out. I'm just going to plot all of them, PTP out, and a line width of 2. Let's see, grid on. I don't need a hold on. I need an X label, time, and this is going to be a Y label of angles in radians. Actually, I didn't convert to degrees, I don't really care. And then I'm going to copy this and then plot not quaternions, the angular velocity, and do fig 5, and then PQR out, PQR out, and do angular velocity, and that's radians per second. And so let's just make sure this plots. So we should just get, didn't like it. PQR out is not defined. Is it just PQR? Oh, that's why. Yeah, okay, so PQR out. Run that. You know, I have a simulation started here. I should put a simulation complete just for kicks. So there's the norm. So there's angles and then angular velocity. Okay, so let's, what was I going to say? Let's do a simulation complete. Let's see, display, simulation complete, and then let's, that's fine. And then, what was I going to do? Oh yeah, I want to rotate the satellite now. So let's rotate the satellite at 1 radian per second. Translational dynamics should be exactly the same, but we will hopefully see one of the axes rotating. And it looks like it's running a lot slower now because the whole system's rotating and it's probably freaking out, so it's changing the time step. Eventually, I think we're going to need to move to a fixed step integrator, but I'll leave that for another video. Oh wow, this is really cooking now. I also feel like we need to drop down the, once we move to a fixed step integrator, I think we can change the rate at which we're calling the IGRF model, because I think the IGRF model is really causing a lot of slowdown, because you don't need to call it that often. You can call it like once a second and it's totally fine. I'm going to pause the video and I'll bring it back once it's ready. All right, and we're back. So you can see that the blue line here is at 1 radian per second, so the system is rotating. And you can see why the time step was so crazy. I think I made it spin too quickly. But anyway, there is a crazy sine wave in here of the system just rotating like crazy. And there you go. So I'm gonna call this video done. Rotational dynamics are in and they are working. And in the next video, I am going to do the sensor model, which is gonna include switching to a fixed up integrator and adding in noise to the sensor and then the complementary filter to filter out that noise once we add it. Okay, hope you enjoyed this video and see you in the next one.